Hi, hi everyone. My name is Diogo Gonçalves, and I will present our paper named Dynamic Network Slicing in Fog Computing for Mobile Users in MobFogSim as part of the International Conference on Utility and Cloud Computing. This work was made by me, Diogo Gonçalves, Luiz Bittencourt, and Edmundo Madeira from the University of Campinas, Carlos Pugliafto and Enzo Mingozzi from the University of Pisa, and Omer Hanna from Cardiff University. Nowadays, the concept of Internet of Things is very popular. Several devices such as mobile phones, drones, smart home devices, or communication technology embedded in vehicles has been present in the day of the people. However, most of these devices offer a low amount of computing and storage resources, which limit them to run simple tasks. A common solution to surpass that limitation is to move the computation of these devices to the cloud. However, in many scenarios, the user requires lower latency, and then the service that the user is accessing needs to be as close as possible. And that's become a problem for the infrastructure to serve these mobile users. Once a mobile user starts to move from the infrastructure needs to migrate the services to a place closer to these users. Thanks to some technologies like SDN and NFV, the concept of network slicing have been developed to provide a more flexible infrastructure. Network slices are a virtual network running over the same physical infrastructure. Based on that, we can create specific virtual networks to serve users with different requirements. For instance, we can create a slice to serve users that require low latency, another slice instance to serve users that require higher throughput or a specific network topology. Our research group have been working on problems of service migration associated with user mobility on fog infrastructures. To evaluate these scenarios, we developed a simulator named MobFogSim, which is open source and can be found in my GitHub page. Also, more details about the MobFogSim can be found in our paper in the journal Simulation, Modeling, Practice, and Theory, which we introduce the simulator. In this work, we extend the MobFogSim to support network slicing. Then, we are providing a simulator to evaluate network slicing in the context of service migration on fog infrastructures. We also provide in this presentation an evaluation of the impact of the dynamic network slicing on that scenario. Before starting to explain the contributions of this work, we will talk a little about our simulator. So MobFogSim is based on CloudSim and iFogSim, which are popular fog and cloud data center simulators. MobFogSim extends these simulators by introducing mobile support for IoT devices. Then MobFogSim evaluates the impact of the mobility of the users in the context of service migrations. Different migration techniques can be evaluated in our simulator, such as code and live migration. Some classes, mainly related to mobility and migration, were created in our simulator, and other ones were modified to reach mobility support. Another improvement in the MobFogSim is the possibility to deal with realistic mobility patterns. We can use realistic mobility datasets as input to our simulator. That process can be made by an offline synchronization with Sumo, which is a popular traffic simulator. In our previous work, we simulate a scenario with 100 different users using realistic trace from Luxembourg dataset. To evaluate the impact of this user speed, we create two more datasets based on the original ones. These datasets were 2 and 3 times faster than the original dataset, keeping the same route. We simulated these users in two different network conditions, which we named faster and slower network. These network parameters were based in a real testbed. In general, we can see in the left plot that faster users present higher latency if compared with the original dataset. That problem is even worse if the users are accessing a slow network. That can be justified if you look to the number of migrations in the second graph, represented by the red and blue lines. Faster users have less time to commit their migrations, which results in let their service further from the users. Based on that scenario, we can think of the network slicing for introducing traffic priority for faster users. In general, we can generalize the role of network slicing for every group of users which require an special condition in fog. Based on these scenarios of users with different requirements and different mobility patterns, we can see network slicing as a promising solution for fog and cloud infrastructures to provide a proper network condition for these users. However, how does network slicing perform the service migration in such a scenario? And more than that, how can we validate it? To best of our knowledge, there is no another simulator that combines user mobility, service migration, and network slicing support in the literature. In this work, we introduced the network slicing support on MobFogSim. At this moment, we model the slicing on the network resources. More specifically, the link bandwidth and the network topology. MobFogSim models the slices instance over the same physical infrastructure. Each slice reserves a pool of virtual resources, which is defined by the dedicated bandwidth from a set of the links. We also create some mechanisms to define the slice instance to which the users belongs. Based on that, we can grant access for different groups of users to a specific slice instance. In our validation scenario, we model an infrastructure with 2 fog nodes and 2 slice instances. The users are connected to these fog nodes by a wireless interface. In this scenario, the users are moving from a fog node to another one, and then the infrastructure will perform a service migration. In this scenario, each user is connected to a virtual machine. The network parameters were also based on a real testbed. The containers that run the user servers on the fog has 128 megabytes, which will be migrated through a 74 megabits per second link that connects the 2 fog nodes. At this moment, we are not using a realistic mobility pattern. In these experiments, 20 users are starting from the same point and move with a constant speed in direction to the second fog node area. We evaluated this scenario based on 2 different variables, the number of users allocated on a slice and the amount of resources that the slice has available. In the first one, we simulated different users distribution among slice 1 and 2. We allocated 2 users in the slice 1 and the remaining 18 users in the slice 2. The another scenario, 4 users in the slice 1 and 16 in slice 2. And the last one, with 80 users in the slice 1 and 12 users in the slice 2. We also made the resource distribution in different scenarios. The first one, we allocated 10% of the resources for the slice 1 and the remaining 90% for the slice 2. In the second scenario, we allocated 30% of the bandwidth for the slice 1 and 70% for the slice 2. And in the last one, we allocate half of the bandwidth for each slice. In the left graph, we can see the time needed to proceed with the migration process. The blue line represents the slice 1 and the red line represents the slice 2. In this scenario, where 90% of the bandwidth is dedicated to the slice 2, the users in that slice instance perform the migration process faster than the users in the slice 1. In this scenario, we are giving more priority to users in slice 2. As a collateral effect, the users in the slice 1 are performing so much worse in the migration process that probably those users are not reaching the minimal levels of experiment. And that result is even worse if you increase the number of users that are allocated in that slice. In that scenario, where we provide half of the bandwidth for each slice, the slice 1 as it serves fewer users than the slice 2, are performing faster servers migration than the slice 2. In the second graph, you can see another metric we used to evaluate the performance of the slice instance. You can see that the slice which receive fewer resources stay active during the service migration until the ending of our simulations. On the other hand, after one slice finish all its migrations, the resources allocated to that slice becomes idle. In that third graph, we can see the amount of data that could be transferred while the idle resources were not used. For instance, slice 2 received 90% of the bandwidth to serve 12 users. Finish all its migration request much faster than the slice 1. In that scenario, 80 gigabits could be transferred while the slice 1 stay active finishing its migration after slice 2 finish its once. This is a typical problem of provide dedicated resources for some network. In this scenario, dedicated resources are subject to be idle. However, network slices can scale up or scale down as demand. And our simulator has the capability to support the reallocation of network resources along with the simulation. Based on that, we provide a second experiment with idle resource reallocation. In this second experiment, once one of the slices finish its migration request, its idle resources are relocated to other slices to boost its migration process. In the left graph, only slice 2 can lend its resources. But in the left plot, we evaluate a scenario where only the slice 2 can lend its resources. So, in the scenarios where slice 1 finish later than slice 2, it receives the idle resources from slice 2, which helps it to perform the remaining migration requests if we compare it with the previous scenario. However, when slice 1 finishes earlier than slice 2 continues to perform as badly as the previous simulation, where using a static allocation. In the right graph, we can see what happened when both slices can lend the idle resources to the another one. In this scenario, it's possible to see that the slice that received a higher priority in our simulation in terms of number of dedicated resources or reduced number of users still perform faster migration services and finish all its migrations earlier than the other slice. However, no idle resources was wasted. That idle resources relocation helped to the slower slice to finish their migration earlier than expected. The resource reallocation of network slices can provide better utilization of the resource in the fog. However, that slicing reallocation presents a computing overhead that was not evaluated in this work. That computing overhead has a direct impact in the reallocation frequency because if that reallocation is cheap to the infrastructure, there is possible to do many reallocations as the infrastructure judge as need. However, if the process has a high computational cost or a long time to finish that process, the reallocation may not be suitable for some scenarios. For further evaluations of the dynamic slicing are needed to provide the impact of dynamic slicing over time after several reallocations. Another aspect that was not evaluated in this work is the dynamic slicing on not only idle resources. Furthermore, in this work, we evaluated the impact of the dynamic slicing, taking into consideration only network resources, like bandwidth and network topology. Other resources, such as computing and storage, could be evaluated in future works. Finishing our presentation in this work, we introduced MobFogSim as a tool for simulating network slicing on fog computing. As present in our experiments, network slicing can introduce priority traffic for some users, which can improve the performance of the service migration. Furthermore, we can see how dynamic network slicing increase the resource utilization if we compare with the static allocation. However, we made this note that the network reconfiguration is computing overhead dependent. These are the references that we use in this presentation. And I would like to thank you for your attention. Any questions, feel free to contact me. So, bye. Thank you.